Hello and welcome. I was not expecting to make a video tonight. However, I've been pulling stuff out of storage and amassing a pile to take hopefully to the flea market this fall, if indeed they have a flea market. And I pulled this Boonton 260 AQ meter out, and before I sell anything, before I take anything to the flea market, I like to go through it and make sure everything's working correctly, so when I sell it I can say yes, it works 100%. I have kind of a rep up there. People who have bought from me before know me, and since I'm there, or I used to be there twice a year all the time, I don't sell anything unless I can say definitively if it works correctly or not. I hate it when you buy something, the guy says, oh yeah, it works perfectly, and you get home and you look inside and you find out that, somebody's been in there cobbing stuff and there's no way on earth it ever worked. And of course they never show up again at the next flea market. At any rate, enough soapboxing. I pulled out the 260A here and I was playing with it, just refreshing myself on the idiosyncrasies of how it functioned. And one of the bands was dead. Of the 8 bands, 7 of them worked and the 8th one didn't. And this happened, I don't know, 3 weeks ago, I guess. I pulled the tube out of the oscillator just for the heck of it and tested it, and it was way down in the middle of the bad range on emission. I doubted very seriously that's the problem. I've seen these tubes work all the way down to where they're not even hardly moving the needle. They'll still function, but I said, oh, what the heck. Before I dig into the thing, I'll order a spare oscillator tube, and in fact I ordered 4 of them. It takes a 5763 beam power tube, and they're fairly common. They're just a nickel dime part that you can pick up anywhere. I bought 4 of them so I'd have some extras in stock. And this afternoon I said, oh heck, I'll throw that oscillator tube in and see what happens. I wasn't expecting anything good to happen, and sure enough it didn't fix anything. I didn't think it was gonna. So I started to dig into it and I said, oh heck, while it's on the bench, why don't I just make a video about it? It's an interesting design in the oscillator. Let me move the camera here, it's going to get a little shaky. There's a turret inside of here. And as you change bands, the whole turret moves. And all your oscillator coils are mounted on the turret. And as you change bands, I don't know how well this is going to show up black on black. Oh, it looks like it's going to be just fine. Whoops, almost dropped the camera again. Is the focus hunting? Nope, looks okay. As you change bands, you can see the windows change. Actually, that doesn't look like it changed, but there's an arrow here. Now there's an arrow here, so there's 2 bands in one window. And 2 bands in one window here as it changes. Nope, we're going to jump down here. Then the next one should have an arrow in the upper section. It's quite a system. And as you probably know, Hewlett-Packard bought out Boonton. In fact, the last couple of production runs of this 260A were actually painted Hewlett-Packard gray and had the Hewlett-Packard logo on them. So Hewlett-Packard considered it a pretty good design. This thing's a 1/4 of an inch thick. Well, actually, it's almost 5/16 of an inch thick here. That's a 1/4 of an inch, and that's a 1/4 of an inch cast aluminum that the oscillator turret is mounted in. They do that for stability. At any rate, I've got a dead band, and I suspect a coil has gone open. The first thing I did, I cleaned up the pins on the connection. There's a bunch of like finger stock connections that connect to a particular section for that oscillator, and this happens to be the section that's not working. However, you have this set of pins is connected, and then 2 pins here and 2 pins here are connected, and what they're doing is shorting the 2 adjacent coils so that you don't end up with a wave trap at a second harmonic. Pretty clever design. The finger stocks are known to give an issue on this. The finger stock clips are one of the weak points of this design, and everybody, you know, says, oh, you just have to clean the finger stock. Well, I've done that and it didn't fix it. So now we've got the schematic out, and I'm going to go through and check continuity. These are your coil sets. This one is the one range 4 that has the problem, that's dead. What's interesting is on the side of this it says B5, band 5. I think they're indicating that the 2 trimmer caps are for band 5, but I don't know. I went into position, I verified this several times, made sure I was on the correct band, went around the other side of the unit, marked the band I wanted, and then moved it up here. So I know for a fact that's the set I'm after. It's not functional. That is band 4, the 700 kilohertz to 1700 kilohertz band. What I'm going to do is ohm out all the coils. I can ohm out from here to here. Then there's a connection where there's a 680K going to the next coil set. There should be continuity here to here, up through this coil over to section 8. From there, there should be another 688K resistor going down to pin 2 on the set on the other side. So I'll ohm all that out. If all of that checks out, then I'll get out my capacitance bridge and start checking. There's a capacitor from between pin 4 and pin 7. This one's going to be a little tough to figure out, but there should be at least a 1500 ohm resistor across there. So let's get going here. I've already figured out the numbering scheme, and it starts from the right and goes to the left. 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to get the ohm meter set up, and we'll start digging into this and see what happens. Okay, we appear to have everything in frame. I hope this is going to work out. Maybe I'm going to have to change chairs. This one's kind of creaky. I hope the camera's not focus hunting here, is it? I don't hear the motor cycling, so I don't think it is. I've been looking for a new camera, sadly. I don't want to give up on this one. I love this old camera. But I can't find one that's got the features I want. In fact, I'm thinking of doing a short video on that, demonstrating the features of this camera, and see if anybody out there knows where there's something compatible. But that's for another night. Tonight I want to get this thing going so I can get it into the flea market pile. Let's see here. We should have... Can you see that? Good. We should have continuity between pins 1 and 2. Then we should have 688K to pin 8 to the coil next in line. Actually, these are reversed, I think. This one. Yeah, there's the 688K resistor. So this is the band we're working on. Then we'll go down here and check the continuity of that. Is that right? Yes, that's right. Okay. Don't let me get lost, guys. Keep tabs on me, alright? We should have an inductor coil between there and here. What do we got? Oh, these 2 pins here. I had this wire in the way. I didn't see the next pin. There's pin 2. Yes, we have continuity there and there. So that one, I'm going to take a little orange pencil and mark that out so I don't get lost. You get to a certain age, you have to leave a trail of breadcrumbs so you can get back home. Let's, where am I here? Okay. So 1 and 2 have continuity. Whenever I have a piece of equipment like this, I usually copy the schematic out of the manual so that I'm not playing with a 70-something year old manual. 73 years old, I think. I think the date code on here was 1947. Oh, which brings up another point. This filter capacitor right here, I believe, is the original. The solder connections have never been disturbed, as far as I can tell, until tonight when I disconnected the ground side. I did some tests on that capacitor. It's well within tolerance on the capacitance. The ESR is excellent. It runs at 300 volts during operation. It's a 450 volt cap and it's running at 300 volts. I set it up with 375 volts. I went 75 volts above its normal operating volt. It's, operating voltage in this unit, still within its safe range, and let it sit for about 15-20 minutes. And it only had, it had 400 microamps of leakage and was falling. It's as good as a brand new cap practically. That's twice in a row lately I've had old electrolytics that were fine, so I'm just going to leave that cap alone. It's got no signs of leakage. None of the rubber seals are cracked. It's just in incredibly good shape. Again, this is Boonton, Hewlett-Packard quality equipment. So anyway, let's move on. And I know I'm going to get yelled at for leaving that cap in there. That's all right. It's mine. Well, it won't be mine when I sell it, but I'll let the guy know. Let's see. We have to go 688K to pin 8 from pin 1, so I'm going to have to range up. No, we're on the 10K setting. Actually, I should check that continuity in a lower range. Still have continuity? Can you see the meter? Yep, good. Okay, let's go up on 10K range. Pin 8. What do we got, guys? I can't see the voltmeter from here. Oh, 68 on the money. On the money. And before anybody says I can't be that accurate with this voltmeter, I put the resistors in it. They're better than 1/10 of 1% on the resistors. I sat there for hours with a very, very expensive Hewlett-Packard ohm meter that goes out to milliohms, mixing and matching series parallel resistors when I rebuilt that VTVM. And that thing is just about as accurate as you can get until you get into a digital meter. Okay, the 688K is good. Let's put an orange line on that. Continuity there. So that brings us here. Is the orange showing up? I don't know if that's going to show up on the camera. Yeah, I guess I can see it in the viewfinder. So we've checked this out. We've checked this out. What are we going to do next with an ohm meter? Okay, I can go on pin 3 to pin 4. And then I should have continuity to pin 8. And then 68K down to pin 2. 68K. Oh, the other one's 680K. This one's 68. Okay. So I'm going to do 3, 4, and 8. And let's go to a lower range. Times 10 should be good enough. Let's take this off of here. Go on to pin 1, 2, 3. And pin 4 should have continuity. Good. Or not so good. I'm hoping to find something wrong here, or I don't know what I'm going to do if there's no break anywhere. Although, according to what I've read on the internet, it's common for these to fail. I did go in there and poke around, and I can't find anything loose. Pin 8. Pin 8. 1, 2. Oh, pin 8's the last one. Do we have continuity? No, we don't. Aha. My. And that's the adjustable coil. That's the one that's got the slug in it that's open. 1, 2, 3, 4. Yes, that's good. Check the meter. Check pin 8. Nothing. Looks like you found it for me, folks. Well, thank you for watching the meter for me, because with this in front of me I can't see the meter. You're looking at the meter over on the side. This thing's still recording. It's awful quiet. I'm not hearing the focus hunt. Yep, the timer's running. Usually I hear it when I put my hand in front of it. No, I'm not hearing anything. No, I don't hear the motor, the focus motor changing. I hope it's focused. So, okay, 3 and 4 was good. 4 and 8 isn't. Now I've got to figure out how I'm going to dig into there and get to that. I don't know how to get that out of there. I don't want to take the whole turret out. Oh, you clever son of a guns. Well, it's still going to be a chore. 1, 2, 3, 4, 5, 6. This is connected with a plug. Looks like I can drop the whole oscillator block unless I'm not seeing something here. I disconnect that coax. I don't know if you can see that. That's the coax that goes to the thermocouple. And this is the VTVM that measures across your parallel resonant circuit and gives you an indication on the top meter of your Q. So it looks like if I pull this connector, one knob, 6 screws, it looks like this whole oscillator section will come off. And oh, what I got excited about just a second ago, let me put the camera back up here. This section of the oscillator coil, there's 2 screws holding it here and 2 screws holding it here, and I'm like, how the devil am I going to get that out of there? Well, let's see if that shows up on the camera. Let's see if I can get the angle right here. We've got an access hole right here that lines up with the 2 screws on this side, and there's you probably can't see it. There's another access hole on this side that goes through the casting, so I can get the screws out from that side. Somebody was thinking. That's what I love about old engineering. People fought back in the day, not like the kids fresh out of college today that have never built anything. These guys were hands-on people. So what I'm going to do, actually I'll have to pull 2 knobs, I lied. Oh, maybe 3 knobs. No, that's a pot. No, that's a trimmer, that goes inside as well. So I'll have to pull 1, 2, 3 knobs, 6 screws, and 2 connectors, and that whole block should come out so that I can get to the 2 screws that are behind this panel. So let me get that done, and we'll pick up from there. Okay, I think we have it. I didn't have to take the turret out of the machine. By rotating it up here, I was able to get in to the end. Clipping on lead, this number 4 pin, I could go in and touch the wire on the coil on this end, and I could see continuity here, so I knew this solder joint was good. And even though the wire was attached here, I couldn't get any continuity. When I touched up the solder joint, I could see the end of that very, very fine wire on the inductor was very, very corroded. I cleaned everything up, I put flux in there and cleaned everything and tried to resolder it, but the wire just crumbled apart on the very end. Fortunately, this connection underneath here goes up on a jumper to this terminal here, so I moved the wire up to the top. It's only moved it 1/2 inch or so. I might have to retweak the tuning, but this is a fairly low frequency unit. I shouldn't have affected the tuning all that much. And if I touch this now, you can see we've got continuity through that coil. So let's turn this puppy on and see what happens. I'm going to have to move the camera to lay this thing down. Bear with me, folks. Okay, is the camera running? Yes, it is. Is it searching for focus? It doesn't appear to be. Good. Okay, moment of truth. Turn the XQ course down, or very low. What usually happens to these is people don't know how to operate them, and they leave this course or turn this course control all the way up. this machine is supposed to have a power switch here. Somebody replaced it years ago with a toggle switch, which makes it very dangerous, because if this gets turned up and you flip the toggle switch on, you'll burn up the thermocouple. And I'll go over that in a minute. But we'll turn it down low. We'll watch this meter. If that meter, whoops, let's go on the right band. I'm so happy I didn't have to pull that whole thing apart. Okay, that's the band that was dead. Let's turn the switch on and let's see if we had a reading on this meter. If we do, we have success. Keep your fingers crossed. Hope the oscillator wakes up. Come on. Come on, you can do it. Oh, come on, work. Oh, look at that. We're in business, folks. The way this unit works, the oscillator puts out a fair amount of RF. That tube, they say that it'll do almost 12 watts at these frequencies. It sends the RF to a thermocouple. The thermocouple heats up a thermistor. The thermistor puts a reading on here, and your cal point is up on number 1. The reason they did it this way, rather than just using an RF voltmeter, to have an RF voltmeter, there's no ALC in here. And of course, let me turn this down so I don't burn up the thermocouple. When you change frequencies, you see the meter going up and going down. As you change frequencies, the voltage in your resonant circuit changes. There's no automatic level control in this system. So you kind of have to ride shotgun on this. But because the RF level changes with frequency, if you tried to use just a voltmeter, it would have to be frequency dependent. It would just add all kinds of complications to the circuitry. So they put the RF across a heating element in the thermocouple unit. That's not frequency sensitive, at least not up through 1700 kilocycles it isn't. This will go from, or up through 50 megacycles it isn't. This will go from 50 kilocycles to 50 megacycles. Having a thermocouple, which is not sensitive to frequency, means they can have a meter that will always read the correct wattage level or output level from the amplifier. Of course, you have to trim the level all the time. Let me see it. Am I explaining this correctly? Watts are watts. Current and voltage across a resistor, it doesn't matter what the frequency is. Watts are always watts. So up through 50 megahertz from 50 kilohertz, just heating up a resistor on the thermocouple, and I shouldn't have said thermistor, I misspoke there. There's a thermocouple across a resistor. I think it's a half ohm is what the book says. It heats up this precision resistor, which heats the thermocouple. The thermocouple reads on this meter, and because it's not frequency dependent, it's always going to give you an accurate indication of the same level of RF output. How's that explanation? Is that better? I got my turds twisted. So now that that's working, I should be able to throw an inductance on here, and we should be able to read Q. Hang on while I go get, I just want to say this before I forget it. If you have one of these, every time you see the caution here, every time you change bands, every time you change frequency, turn this down to some, maybe half scale, so that when you change frequency, see how the needle's coming up? On some bands, the oscillator is extremely active. On other bands, not so much. If this is turned up and it's sitting on 1 and you flip to a band that's more active, or you flip to a frequency that's more active for the oscillator, before you know it, this needle can run off the end of the scale and you've burned up the thermocouple. The thermocouples are made of unobtainium. They do not exist anymore. They are gone. They are done. There are none. Was it General Radio? No, I'm trying to think of the outfit. They do manuals. In fact, I think it's right on this manual. It says and it's an instrument shop. No, I had a book around here with the name of the company on it. At any rate, they had one listed on their website about 5 years ago, one of the thermocouple units, and they wanted $200 and something for it, and it was the only one in existence that anyone knew of. And that's gone. They don't have it anymore. Let's see. I've got to remember how to run this thing now. It's been so long. This, execute fine, 0 just. Here we go. So I set the Q meter to 0. When I get my coil, I'll set this to the calibration point. Bear with me. Okay, I have a working coil. They call these working coils. Plugged into the unit. There's a variable capacitor here. In fact, you can measure capacitance on this bridge down to 1/10 of a picofarad, and it's pretty accurate. It's a little bit tedious to do. It's not its primary function, but it is in its bag of tricks. You can actually measure capacitance up, and it's not a great range of capacitance. It's up through several hundred picofarads, but you can measure it down to a tenth of a picofarad with this. Getting off subject here. Let's see if this thing will resonate. There should be at some point. Yep, there it is. There's a peak. Okay, Q of 150. I'm going to turn this up, and that meter is going to probably go off. Nope, it didn't go off scale. It stayed on target. Okay, we line up with the 1. Never go into the red zone. Never ever go into the red zone. And I'll peak that, and we're looking, that coil has a Q of about 230. Now, I don't know how close it is to its stated value. It says Q approximately 200, so the meter's working fairly well. The Q is 200 listed on here. This is saying 225. It's working. It's working just fine. Now, you can see by doing this, I am affecting the tuning of the circuit. I've added some inductance or capacitance, probably because of my hand. If I get close there, I'm not even touching it. That's just capacitance. I'm affecting the tuning. If you put a capacitor on here, let's see if I have one. I should have one. Actually, I'll want a capacitance that works at the resonant frequency of that coil. I'd have to search around for the right value. But if you wanted to measure the capacitance, or not the capacitance, excuse me, the Q of your capacitors, say you wanted to do an A-B comparison, and I did this a couple of videos ago on my other Hewlett-Packard unit, to check the difference between, say, a 005 of this type and a 005 of this type, you'll find this has a much higher Q. It's a much more efficient capacitor. They're used, you want to use this for coupling, interstage coupling, and you want to use these for bypass, RF bypass to ground, because they're very lossy, they have very low Q, and they do a very good job of bypassing to ground and dissipating that RF you don't want. However, you don't want to use these for audio coupling. You want to use something with a high Q that passes on the signal much cleaner and much more efficiently. What else did I want to do with this thing? It's up and going. I should probably tell you the gotchas on this. If you want to buy one of these units, if you see one of these units, before you buy one of these, let me turn this down. I'm going to take this coil off of here. If you're talking to somebody via email, tell them to turn it on. Tell them to turn up the XQ course, and then caution them to be careful, because they're probably not going to have a clue how this thing works. If this will read upscale, that means the thermocouple and the oscillator are good. Anything else in here you can fix. These things are what do you call them? Jelly bean parts, except for 2 items, and I'll show you the 2 items that are not jelly bean parts. If you're looking at one of these and it will read on this bottom meter, go ahead and buy it, because anything else you can take care of, you can fix. And I'll show you what to look for here on the back. And I think I did this in one of my other videos, but it doesn't hurt to repeat this part. Cord's in the way. Let me unplug it. Never mind. I'm just going to slide it over. There's two items that go bad on these, and they go bad all the time. Am I in frame? Okay. I'm going to turn the camera over here. In fact, maybe I should just bring it in closer. Excuse all the handheld camera motion. And we'll do this. The most fragile part of this unit is this little block right here. This is the thermocouple unit. This is the part that has a precision half-ohm resistor as a heater and the thermocouple that makes that bottom meter read. If this is dead, pass the unit up. You'll never find one of these. They don't exist anymore. Having said that, there is a couple of other things that might be wrong and not make it read. If you can look at the unit personally, or get somebody who's trying to sell one of these, if the guy has half a brain, ask him if he has an ohm meter. And you can pull this cable off and measure for, boy, this one's been on a long time. You can pull this cable off and measure from the center conductor to here. If there's continuity, this is probably okay and there's something else wrong. The oscillator's not running. Don't worry about the oscillator. You can fix that. That's not a big deal. You just saw me fix it. And there's dozens of these out there that don't work. If you need parts, you can scavenge parts out of the turret. So if it has continuity internally here, the thermocouple's probably fine. The second part that's unobtainium, or very, very rare, is this tube. That tube was custom made for Boonton. They had the grid custom calibrated, if you will, so that the meter, the upper meter, voltmeter, this is a VTVM basically is all it is. It measures the voltage across your tuned circuit, your resonant circuit. It's basically just a VTVM, but it had a specific curve. Boonton used to hand pick these tubes. I think in the beginning, I'm told that they took 1659s and they used to go through dozens of them until they found one that had the right characteristics, until they got RCA to custom make the grid in tubes. And they used to make, it was called a 535-A, and that's what's in here is a 535-A. It was custom made for Boonton. However, the 535A is just a tweaked version of the 1659, also known as a 2A6. So the 2A6, the 1659, or the 535A will work in here. Now the 1659s and the 2A6s are somewhat rare, but they do exist. It's probably going to cost you $20 or $30 to get one of these, maybe more depending on how rare they are these days. The calibration will be off. The curve won't be correct for the Q reading. For our purposes, we don't care. You and I and whoever else is going to buy one of these, you're not going to be using this in a calibration lab somewhere trying to get, specific Q readings. All you're going to be doing is an A and B. Is this coil better than this coil? Is this capacitor better than this capacitor? How many picofarad is this capacitor down to the 10th of a picofarad? You can do all of that even if the curve isn't correct. The meter will still read. You'll still be able to find peak. You'll still be able to do A-B comparisons, one coil or one capacitor to another. The Q function will work. It just won't have the exact calibration curve that Boonton had. They wanted every one of their units to read the same. When they plugged in a coil, if it said 230 on this unit, they wanted it to be 230 on the next unit and 230 on the unit after that. They're an instrument company. It's what they did. You just saw this one work. This says a Q of 200. It was reading 200 and what, 25? I don't even remember. it doesn't matter. We're doing A-B comparisons. Is this cap better than this one? Is this air cap better than this air cap? Is this coil form that I'm making my coil on any good? In fact, you'll find out on a heartbeat if you wind coils and stick a piece of black plastic in the center of the coil, the Q will change. If you use PVC, it probably won't. Black plastic is terrible stuff to wind a coil on. You saw what happened when I went to tune up one of the radios using one of these diddle sticks. It threw it out of tuning because this had become conductive. Black plastic usually makes a lousy coil form. There are exceptions. Delrin probably is okay. But with one of these, you can test your coil form material before you wind your coil, whether it's for an antenna, whether it's for a transmitter. If you're doing low band work, if you're using Litz wires to make big loading coils, you want one of these because you can test your design to see if one design beats the other for quality, so you get all of you're only allowed, what, half a watt or something? You want the maximum radiation efficiency out of your coils. Should your coil be taller and narrower or wider and squatter? You can wind both, and you can test on this unit which coil is going to be more efficient. Is Litz wire worth using? Is it okay just to use like number 10 house wiring to wind your coil? Or should you go to the extra expense of using Litz wire? There's pros and cons. There's, you ask 10 people, you'll get 10 opinions, but you can find out definitively using one of these units. So that's the two items anyway. I'll stop chattering here before this thing gets too long. This tube can be found. Don't worry about that. This is unobtainium. If this thing is open, pass the unit up, unless you can get it for dirt cheap for spare parts. Okay? Okay. Enough said. Thanks for helping me fix it. I'm the radio mechanic. I'm going to put this back together, and if anybody's going to be at the Deerfield Flea Market this fall, if they have it, and you want a Q meter, this one will be for sale, along with the manuals, the operator's manual, the service and repair manual, the calibration manual, and several of these working coils. I have enough working coils to cover the range of the instrument. I don't have an entire set, but I have enough that you can step through the entire working range of the instrument. These are going for anywhere from $15 to $30 a piece. So the fact that there's a set of 1, 2, 3, I think I have 9 of them that will go with the unit. Okay guys, that's it. I'm going to wrap it up. I'm going to try to get something else done tonight. I'm so happy that this is up and running again. We'll catch you on the next video. In fact, I think I'm going to do... excuse me. Easy for me to say. I think I'm going to do the next video on my camera hunt. Catch you later. I'm the radio mechanic. Bye-bye. Okay, a little bit of bonus footage. Got 3 capacitors here. This is either a ceramic or a glass tubular. I don't know which. Could be either. A disc ceramic and an orange drop. And all 3 of these are the same value. I'm going to put them in the Q meter. And I I had a bit of a surprise when I ran through this before I shot the footage. I would have bet my paycheck that the glass tubular would have been the highest Q cap here, and I would have given up my paycheck. So let's take a quick look. We'll put the orange drop in here and resonate it. We're on our number 1 calibration line. It's crept up a little bit as it warms up. There we go. Our meter is zeroed. I gotta find a resonance. There it is. All you do is go for the peak of resonance. And that's got a Q on this meter of 80. Now that's with this coil. If you change coils and change frequency, you're going to get different results. Q is frequency dependent. depending on the device. Some devices will go up in Q, some will go down in Q. Frequency rises and falls. It's frequency dependent. And again, I've said in the last video, this is an A-B comparison. We're not looking for an absolute value. Q is a valueless number. It is there is a formula to determine it. It doesn't matter. You're looking for A versus B, which is better. Okay, that's what you're going to do. This is not a calibration lab. So we have a Q of 80 with that capacitor. So let's say you're trying to determine which one you should use for your audio coupling or your RF coupling. You're going to want to do it at the frequency you're working at, of course, as well. But right now we're working at, we're on this range, about 700 kilohertz, give or take. Very close to 700 kilohertz. We'll put this one in here. Now I'm going to have to retune a little bit. These capacitors, while they are the same marked values, this circuit is sensitive enough you have to repeak it. And I've just got to find where that one, there it is. Okay, the other one was 80. And here's where I would have lost my paycheck. This is 72, 73 versus 80. So the orange drop is actually a better capacitor than this glass tubular, which shocked me. I was just amazed. Now we'll take our old friend, the disc ceramic, and again, same value capacitor. We'll put it in there and we'll resonate that one. And the needle hardly even moves. So we'll go to the low Q. We're looking at a Q of 24. So a Q of 24 versus a Q of 72 to 73 versus a Q of 80. That's the cap I'd use for my audio coupling for sure. Okay, more bonus footage. I've made an inductor and I've resonated it. Right now it's got a Q of 150. You can see if I bring my hand near it, I detune it. You don't need to buy these every time. You can make your own inductors. There's nothing other than the fact that these are very stable. If you have a good ceramic core, you can wind any value you want instead of spending the money on more. It's just your time and labor. Okay, let's say I'm building a coil. I'm winding it for 30 megahertz. Now, you guys remember I had a diddle stick the other couple videos ago that was detuning my IF, and I had to go get a new diddle stick because the old one had gone bad, probably too much chemical exposure. But here's two black plastics. Would either one of these make a decent coil form? We don't want to build our coil and just have it floating in space. We want to have it mounted rigidly on something. So what are we going to wind it on? Well, let's try this piece here. Remember, 150. I'll just put that in the coil. It went to 50. I would never wind my coil on this type of plastic. Here's the other diddle stick. Still a black piece of plastic. It barely even moved. Now, you've probably heard that wood is a good insulator, or a good coil form. In some cases, maybe. But let's put a wooden pencil in there, and this is a colored pencil. I don't know what it has inside for. Oop, right out the back. Oh, here's wood. Haha. Did I knock my coil off? Yes, I did. There we go. Oh, let's repeak. There we go. That dropped it almost, well, it dropped it worse than the black plastic did, actually, which is kind of surprising. We're back on 150. Yeah, that's actually a pretty good piece of plastic to make a coil form out of. I don't know what that is, but you could do it with PVC pipe. You could do it with ceramic. You can do it with anything you're going to wind your coil on. You can test it to see if it's serviceable. Now, you've probably heard, I just knocked it out of resonance again. You've probably heard that if you want to make test plastic for RF, you can put it in the microwave oven with a cup of water, and if the plastic gets hot, it's no good. Well, that's great, but what if you got 3 different plastics and you're not really sure which one would be better? None of them may get hot in the microwave or very warm. They may pick up some ambient heat. If it gets red hot and melts, it's no good. But if it just gets mildly warm, 2 of them get mildly warm, which one's better? Well, here's your test. and I just knocked it off resonance again because I keep banging into it. I got to be a little more gentle. So we'll lay that one in there. That one's fine. Here's the other one. Drops it way down to almost 50. So, bonus footage finished. Blah, easy for me to say. Sorry, still not finished. I don't know if you caught the fact I didn't have the multiply by Q. I didn't have the needle all the way up on the 1. You don't have to run this thing at breakneck, you know, pull out all the stops all the time and stress the thermocouple. If you're getting good Q readings at a lower level, you can go 1.5, 1.6, 1.7, anywhere in here, as long as you always A-B comparison at the same level. Let's say you decided to do it at 1.5. You just multiply the reading times 1.5, and as long as every test you make is at 1.5, you'll get a good A-B comparison. You don't have to run the thing wide open all the time and stress the thermocouple that'll never be able to be found again if you burn it up. So you can play it safe. Keep it down at a low level and it'll last for years and years and years. And only for those few measurements, a few times you want to know the absolute Q, would you turn it up. I was getting a 150 and I forget, I'll have to, you know, I was down here somewhere. There's no need to push the thing all the time to the maximum. If you have a reading that goes off scale, then it's necessary to come down to the 1.5 or the 1.6. You turn the level down until you're on the scale, and you could say, like, turn it down until you're on 200, and then you multiply times this for your actual Q figure. Okay, this is really it.